Hi, hello all. I am Shekhar, a MTech first year student in Department of Electrical Engineering at IIT Tirupati. He is here to present a paper titled Deep Back Projection Networks for Super Resolution as a part of Image Processing Lab. Now getting into the details, explaining the problem definition as in the paper, the main aim is to generate a high resolution image from the given low resolution one using deep back projection networks. Extending this idea uh, to dense networks, we can generate dense deep back projection networks which further increases the super resolution in terms of scaling factors such as 8 times enlargement of the original low resolution image. One can observe here the original image from this the low resolution one and the high resolution image, and the high resolution image obtained by deep back projection networks, which is a good satisfactory amount as compared with the high resolution image. Now coming with the details of IEEE paper, this paper titled Deep Back Projection Networks for Super Resolution was published by the authors Mohammad Harris, Greg Shaknarovich and Norimichi Ukita in March 2018 uh, in a research done at Toyota Technological Institute Japan as well as Toyota Technological Institute Chicago, United States. As suggested by the paper, the image super resolution obtained by deep networks can be divided into four types. First one is the predefined sampling. Here one can observe the architecture of predefined sampling. In the predefined sampling, from the low resolution image, we generate the same size of the high resolution image, but the resolution is less. Hence, it is called as a medium or middle resolution, followed by the convolutional layers to lead to the high resolution image. These convolution layers can be trained appropriately using training images, can be tested as well at the last. The main limitation of this can be observed as is it produces new noise in the middle resolution image since it is an interpolation. And the second one is single upsampling. In single upsampling, from the low resolution image follows the convolutional layers, and at the last we upsample to generate the high resolution image of appropriate size. These convolutional layers can be trained as mentioned above uh, by backpropagation by using training images, and it contains trainable parameters of appropriate filter size as well. The main limitation of this can be observed is as it contains it contains a large number of filters and requires lengthy training time as well. And the next one is progressive upsampling. Uh, One can observe here the architecture of progressive upsampling as well. In progressive upsampling, rather than upsampling the image either at the start of the network or at the end of the network, one can upsample the image in different scales uh, as the network is progressing. From the low resolution image follows the convolutional layers, and the image is upsampled of a particular scale, and then follows the convolutional layers, and then the image is upsampled up to particular scale, and then follows the convolution layers and image is upsampled to particular scale, and it can have a many number of upsampling uh, images in the middle based on the architecture proposed or architecture designed by the user. And the high resolution image is obtained at the last by upsampling the image of definite size. One can observe this as Laplacian pyramids as well. And the next one is iterative up and down sampling as proposed in this paper. Rather than upsampling the images either at the start or at the end or of different scales as the network is progressing, one can have iterative upsampling and downsampling images one after the other placed in the network, which is very efficient in propagating or reconstruction error, or generating reconstruction error in the network. This reconstruction error helps in increasing the sampling rate and increases the super resolution features of the image, and gets the super resoluted image at the last or high resolution image at the last, which contains good sampling rate and is of satisfactory or is of satisfied amount as compared with the high resolution image. Now coming to the deep back projection networks or observing the architecture of this deep back projection networks, one can observe the architecture of projection unit and down projection unit as well. Before that, what is back projection? Back projection is an efficient iterative procedure to minimize this reconstruction error. That is, error is propagated from one layer to the other. Observing the projection unit architecture, here LT-1 corresponds to the low resolution image at T-1, that is previous one, and HT corresponds to the high resolution image at present. From low resolution image, by deconvolution with appropriate filter size, we generate a high resolution image. And this high resolution image can be convolved further with appropriate filter size to generate the low resolution image of the same size of the original low resolution image. This low resolution image obtained now and the low resolution image at the start or at the input of the subprojection unit can be compared further to generate the error generated in the reconstruction of this low resolution image after deconvolution and convolution. This error is again deconvolved with appropriate filter size to generate another high resolution image, which is H1 of T. This H1T and H0T are combined further to obtain the high resolution image at the last. The same thing follows for the down projection unit as well, whereas the input is a high resolution image. This high resolution image can be convolved with appropriate filter size to generate the low resolution image. This low resolution image, by deconvolving with appropriate filter size, generates high resolution image. This high resolution image H0T is compared with high resolution image, which is the input to this down projection unit to generate the error, that is ETH. This ETH is convolved with appropriate filter size to generate the new low resolution image. The low resolution image, that is L0T, and low resolution image by error, that is L1T, is combined further to generate the low resolution image at the last. The main thing that can be observed here is the error, that is the error reconstruction error is propagating from one layer to the other here, which helps in increasing the sampling rate and increases the super resolution features. The same idea can be extended to dense projection units as well. In dense projection units, one can observe that as opposed to a projection unit, the input is only the LT-1, that is the low resolution input of only the previous uh, unit. But here, all the low resolution images of all the previous units are considered and concatenated, and followed by the convolution of 1 cross 1 layer is observed to reduce the feature size as the new obtained low resolution image. Then follows the same projection unit as discussed before, and then comes the dense down projection unit as well. All the high resolution images are considered and then concatenated. That is, these are the all high resolution images of all previous projection units, previous down projection units. Sorry, previous up projection units are concatenated and convolved with 1 cross 1 filter to generate new high resolution image and follow the same down projection unit. These are the architectures of dense up projection unit and dense down projection units. These can be placed one after the other in our network architecture to increase the super resolution of the image or to increase the resolution of the image from one unit to the other and to get the required satisfied amount of good resoluted image. Now, observing the network architecture can be divided into three stages. First one is initial feature extraction, next one is back projection stages, and next one is reconstruction. In the initial feature extraction, by 3x3 convolution filters or for 3x3 convolution n number of filters, we obtain n feature maps and then follows the 1 cross 1 convolution to feed into the up projection unit followed by the down projection unit, up projection unit followed by down projection unit as the network progresses. And the high resolution images obtained from these up projection units, that is H1, H2, H3, HT, as if T number of stages are present, we will have T up projection units and T minus 1 down projection units. These T high resolution images are concatenated at the last and is convolved with 3x3 filter to generate the required high resolution image at the last. This is the network architecture. Now coming to the implementation and training details as proposed in the paper, uh, they proposed 2 times enlargement, 4 times enlargement, and 8 times enlargement. For 2 times enlargement in the up projection and down projection units, they used 6 cross 6 convolution layers with 2 threading and 2 padding. And in 4 times enlargement of the low resolution image, they use 8 cross 8 convolution layer in up and down projection units with 4 threading and 2 padding. And 12 cross 12 convolution layer in 8 times enlargement of low resolution image with 8 threading and 2 padding. All these networks are trained using images from DIV2K, Flickr, and ImageNet datasets. These low resolution images are obtained from these datasets by downsampling using bicubic, and they are of size 32 cross 32. Training batch size is of 20, and all these experiments are conducted using Caffe, MATLAB, or 2017 on NVIDIA Titan X GPUs. Coming to the model analysis, uh, depending on uh, scaling factor of a low resolution image, those networks are proposed, and now three networks are considered in this paper. One is the small network, next one is medium network, and third is the large network. In small network, the number of stages are 2, and the medium network number of stages are 4, and L network's number of stages are 6. For t equal to 2, that is, it has 2 up production units and 1 down production unit in the network. And similarly for t equal to 4, it has 4 up production units and 3 down production units in the network. And similarly for t equal to 6, it has 6 up production units and 5 down production units in the network. Uh, Observing the results here, the depth analysis of deep back projection networks for 4 times enlargement of the low resolution image, one can observe here as the iteration progresses or iteration number of iterations increase, peak signal to noise ratio can be observed here. Our large network, that is deep back projection network of t equal to 6, that is 6 up projection units and 5 down projection units network architecture, is performing very good compared to all the existing methods of super resolution as number of iterations increase, generating an peak signal to noise ratio of about 31.59 dB. And similarly, medium network is also able to perform very good compared to all existing methods with peak signal to noise ratio of about 31.74 dB. And our small network is also able to perform very good except to deep recursive residential neural network. The same depth analysis of this deep back projection networks is done for 8 times enlargement as well, and all the three proposed networks are able to perform very good compared to all the other existing methods of generating super resolution image with good peak signal to noise ratio. And one can observe here there is less dB difference as number of iteration progress between medium and large network. Extending the model analysis, comparing with the number of parameters and the peak signal to noise ratio here for 4 times enlargement and 8 times enlargement, one can observe here FSRCNN, that is fast super resolution convolution neural network, has 12K parameters, that is less number of parameters, and has about 30.7 to 8 dB. And our proposed deep backpropagation networks, S network, M network, L network, and DDBN corresponds to dense deep backpropagation networks. Uh, as mentioned by this paper, enhanced deep super resolution network exceeds all the methods in generating the good super resolution images. Our dense deep backpropagation networks with less number of parameters is giving good uh, peak signal to noise ratio compared with EDSR. But for 8 times enlargement with less number of parameters as compared to EDSR, our dense deep backpropagation network is giving good peak signal to noise ratio, which is of good sign. Now comparing the samples of dense deep backpropagation networks at different stages in the network, here considered 7 up projection units And in 7 approximation units, one can observe the resolution of the image is increasing from one after the other at the network progresses. Now comparing the results, some of the results are presented here in the paper. A baby image, the eye of a baby image is taken as a test image. The high resolution image and the low resolution image can be observed here. Different existing methods in generating super resolution image are observed here. One is bicubic, next one is A plus, uh, FSR-CNN, fast super resolution convolution neural networks, and next one is VDSR, very deep super resolution networks, and next one is DRRN, deep recursive residual network, and next one is LAPSRN, which is Laplacian pyramid super resolution network, and next one is EDSR, enhanced deep super resolution network, and the proposed uh, deep back projection. Now our the proposed deep back projection networks for super resolution is uh, giving a good high resoluted image as compared with the original high resolution one in a satisfied amount. The same the almost same result can be observed in Laplacian super resolution network and enhanced deep super resolution networks as well. The same thing is observed in butterfly image as well. The result obtained here uh, is in good satisfied amount and is in good comparable to EDSR and Laplacian super resolution networks as well. Now coming to 8 times enlargement results. In 8 times enlargement, this dense deep backpropagation networks is exceeding all the existing methods. Even without dense, that is deep backpropagation networks, it is also exceeding its performance with all existing methods. Here all the three images can be observed from PSPS 100 dataset, Urban 100, Manga 109. These all three dataset images can be observed. The high resolution, low resolution, bicubic, Laplacian super resolution networks, enhanced deep super resolution networks, I may, and deep backpropagation networks for all the 8 times enlargement results are observed, and it is easily observed from here that it is exceeding all the existing methods in generating super resolution images. Now coming to the conclusion, for all the 2 times or 4 times enlargement, the proposed dense deep backpropagation networks outperforms existing methods except enhanced deep super resolution network. Anyway, this enhanced deep super resolution networks consists of more number of parameters as compared to this dense deep projection networks. And but and then the main disadvantage of this enhanced deep super resolution network is it generates stronger edge which is deviating from the ground truth, and it may lead to or it may mislead the ground truth in several cases. But the proposed dense deep backpropagation networks uh, is almost satisfying the ground truth in a appreciable manner. And but for 8 times enlargement of the original super resolution image, this proposed dense deep backpropagation networks or even deep backpropagation networks are successfully outperforming all the existing methods, even enhanced deep super resolution network, and it also contains very less number of parameters compared to these enhanced deep super resolution networks, which can be real time or which can help in real time implementation as well. This all about the paper presentation. Thanks a lot.